This is a tutorial I wrote for a website a while ago called Creating Dynamic 2D Effects in Unity by Alex Rose. Alright, and this is actually quite relevant to our interest right now. When we talk about water in 2D, or in 3D, we could do this in 3D as well, except we probably want to do a shader for this in 3D. Because otherwise it'd be too expensive to calculate all of this. But let's say we wanted, we'll just for now just do a quick example in 2D and you can see how it would translate over in 3D, even in shaders. Okay, so water, okay, first of all, imagine a spring, right? And it's just like this, right? And it's fixed in a vertical position. And this spring, you can, yank it down and it'll go boing like this, right? Now imagine we have lots of these springs next to each other. Right. Each one of these is a spring. And each one of these can go boing. Right? Now imagine that each one of these springs is hinged at this point with the next spring. Right, so these are all hinged together. Okay. So when one of them gets pulled up, then now there's a force on the other ones. Right? Because originally, I mean, these have stretched out for a start, right? So they were, if we zoom in on here, this was supposed to only go to here. Right? But you see now, this is longer than that. Let me just turn off our Wi-Fi. Right, so this is the hypotenuse, so it's clearly longer. Right? This one's longer. So if you imagine these are springs, each one of these is the natural length, like L. Right? And then this is some value. Here's theta. Right? So this is L cos theta here. Right? And L cos theta minus L is the extension. Right? And so you can see that there would be a tension on here, pulling it inwards. Can I make the thing bigger? Yeah, I reckon. Oop, not that one. Pulling it inwards at, K times L 1 minus theta, sorry, K L 1 minus, oh sorry, cos theta minus 1. Right? And that's pulling this thing down that way. Okay? And then it's also experiencing it in that direction too. Okay, so the left and right forces are actually going to balance. And they may not in time because this might stretch up as well. This one might go up. And so therefore it would be pulling more by the left side. But we're going to assume these things stay in place. So actually this thing is not going to be KL cos theta. That's going to be, if that's theta there, right, then we only care about the downwards component of this, which is that thing. So, that's the force that way. Right? To get it that way, we times it by sine theta. Go on. L divided by cos theta. Wait, let me just draw it one more time. Right, we've got here over here. This is the natural extension L, right? So then, say again. Huh? that's the natural extension of the string, and then in this direction, it's this is L sine theta, and this is L cos theta, right? Oh, and I see what you mean. I see what you mean. Yeah, you're right. You're right. That's L, and that's L cos theta, and that's L sine theta. Yeah, you said it right. So yeah, you're right. You're right. So that thing, you're right. That's L over cos theta. Good catch. Oop. That's L. Luckily, it doesn't matter about this derivation because we're not actually going to use it. But I'm just giving you a more accurate physical description of how it works. Yeah, so this is L over well, yeah, that's L over cos theta times sine theta, right? So that's L tan theta, that. Right? It's L sine over cos. Yeah, it's L tan theta. Okay. So you're right. Instead of this is gonna be we can get rid of that. I can call that L over cos theta. My pen's too big. L over cos theta minus 1, and so this is, well, I can just put the 1 over it, right? That's 1 over that, minus 1. So that's 1 over that, and then that's tan. Can I just check if tan over cos? Wait, sine over cos is tan. So tan over cos is sine over cos squared. Okay, and cos squared is actually, 1 minus sine squared. Is that right? 1 minus sine squared plus cos squared is 1. So 1 minus sine squared is cos squared, yeah. So that's sine over 1 minus sine squared. So that's sine minus 1 over sine. Is it? Sine over... Oh wait, sorry, what you can do is, there's a magical trick. If you've got sine over 1 minus sine squared, you can go, oh, actually, it doesn't even matter. I'm not going to bother going into it. Right. The point is, you're going to experience. This is the force this thing experiences on both sides, right? That's the vertical force. So you could apply this force, right, from this to this, and feel the force that passes between all of them, and you'd end up getting a wave, right? You end up with something that looks like this, right? So I pull down the first spring. Or like, say I've got a rope, right? I got a rope, and I go like this on the rope. Then it will decrease in amplitude over time, but this is going to move across, right? Like this wave that I've added to it moves across here, right? So we start here, and even if I do a small one like that afterwards, it's then going to move to here. If it was perfectly, if it didn't lose any energy, it would propagate like this. This is called wave propagation. Okay. If you want to look more into the physics behind wave propagation in hyperphysics, let me go string wave solutions. Right. You can see this is the traveling wave solution. So this talks about, strings moving in a wave. But the thing is, it doesn't really matter because the way, these are analytical solutions, so we end up with things that look like this. Whereas by the time we've simulated this, it's going to be nothing like this because it's going to be completely arbitrary for a start. We're going to be able to put in whatever wave we want, and we don't want to. it then gets into this horrible series of things called Fourier analysis, which I wonder if hyperphysics has Fourier. It might even be too hard for hyperphysics. Oh, they got Fourier transforms. Yeah, it's just a way of summing waves together in a way that you can figure out, like, you can basically predict bigger waves by putting them all together. Fourier analysis is just like really ugly. You see how this is? You can see there's a wave in here, and there's also a decrease. So there's some kind of like two functions at least here that you can put together. Oh, here's a better example. Right, you know, you got the different harmonics and they work together. Like you got this one on top of the digital wave, and it's making. Well, you can make a digital wave out of a lot of analog waves eventually if you add them all together. You can basically make any wave out of other waves. Is the point of Fourier analysis. Like, see this one, they want just a step function. Well, they just add all of these functions together, and you end up with this wobbly wibbly line that essentially does a sawtooth wave, which is which you use in music, right? Like anytime you hear in music, you hear a song that's like that's a sawtooth wave, right? And this is how they get it on an old school non-digital computer, right? You'd put in all these different waves, and you'd end up getting a wave that looks like this. Now, we don't have to worry about all this stuff because we work digitally. So we can just say, like, hey, I'm going to wibble, oh my god, I'm going to wibble wobble you down. Why is it, oh, my pen's the wrong way around. And we're going to pull everything else up with us. So I'm going to I'm basically going to grab my old code from the past, and we're going to analyze it, and I'm going to talk about how, in many ways, I was wrong. But I mean, I was paid 150 quid or something like this for this article, so like, you know, like I didn't put that much effort into it. Although probably paid less than that for lecturing. Right. Anyway, so let's say we've got right here. I'm gonna show you what I've got. Show me what you got. Right. So this is water. Right. And we're gonna interrupt the water. Boing. Right. Okay, so I stopped this floating eventually. In fact, we can probably repair this lesson. But you can see, and I'll bump this. Boing. So we have a pretty nice simulation of water going on here, right? And look, if I just put a very small one, you know, it'll bubble at all. There are things I don't like about it. You'll see how it immediately, like, goes dunk like a triangle. Especially if I do this, like, it's dunk. There's like that one frame. Wait. Yeah, can I get it big? Why can't I drag this? Yo, just come out. There's like one frame when nearly had it. That. I hate that. It should always that, and I can tell why that is. It's because we're not iterating it immediately. In fact, wait, let me just check one thing. I just want to try one thing real quick. If you'll allow me. I'm gonna take this and I'm gonna apply the code one step. Because update is the thing that moves all the meshes. So this thing has right, we're gonna go through the whole code. First of all, we have a water detector. Right? So when the scene starts, there's nothing. And then when I play, it spawns. And what it spawns is a bunch of meshes. Alright, why can't I really see it? That's weird, isn't it? Okay. You can see each one is a little mesh. Okay. If I move the water, you'll see now that the meshes Well, for some reason you can't really see. Oh, we're on that side, that's why. That's weird. Can I not? Okay. That's just Unity being Unity. Okay, so you can see each one of these is its own little mesh, right? Now, I should have actually combined them to one mesh. And you could do this with shaders, you could do this many ways, right? But you can see that I've cut this into lots of little slices. And then on top of it, there's a line renderer. Okay, so you can see here, this is just one line. And this has got, oh whoa, they added this positions thing to it. That's interesting. Yeah, you can see all the positions here, right? All the nodes. So in here, there's lots of little nodes. So maybe like there. I don't know how many there are. There are 150 nodes, so they're quite small to say you're not really going to notice them. They essentially make a smooth line. But hey, look. Now, oh, that looks weird, doesn't it? That's interesting. It's sort of bouncing. It looks like the bottom is bouncing it up and then to the top line. Anyway, right. So that's how it's made, and when it splashes, what happens is it also creates a collider over the entire thing. So if I grab this, you see there's one big box collider. Well, you can't really see it because it's stupid, but okay, I promise you there is a giant box collider over this entire thing, and that's detecting when stuff drops in. So you can see we're not using a collider because we're using a trigger rather than a collider. I mean, it is a collider, but you know, we got it in trigger mode because we don't want it to stop anything. But if you look here, we've got game objects. I've got this water component, and when something hits it, it causes a splash at the X position using the Y velocity of this times its mass. So we're using its momentum, vertical momentum, times 3, just because, I guess. I don't know what 0 and true are, to be honest. Does it say? Well, we can come back to it in a minute, but something's true and something's 0, so we'll investigate that in a moment. And then on trigger stay, I'm tagging this thing with a float command, which is gonna tell it to float. In fact, it shouldn't even really be on trigger stay. It should just be. Well, yeah, I'll keep it there for now because we'll modify that in a moment. Because there's something I don't like about it. So, first of all, deadly. We don't need to care about that. I ripped this from a game I made, so you could have like acid and lava and stuff. So this deadly ball, which we're not going to be using, we can remove that. Right. So we've got the line renderer. Okay, so that's the line at the top. And then, so you can imagine this whole thing is made of a series of springs like this, right? And each one's dragging each other down. And then these ones make up the line renderer. These points, we store well, they're actually just points in an array, right? Each one there's an array with an X and a Y. X, Y, X, Y. Right? And each one of these drags the other ones around. Right? But they don't drag them left and right. They're all on Y. And then we also take these points and put the mesh on the same points. So if this one moves up, if this spring moves up, right, then the mesh the line renderer goes up, and that mesh goes up, and that mesh goes up. That point. Right, and it's so thin that it's like integration, right? Instead of seeing lots of small triangles or parallelograms, much like integration, you're going to see a smooth line because they're so thin, right? You're going to see, even though it's made of lots of small parallelograms, you can actually notice it for a frame. Like for the first frame, you can see that it's a spike, but for the rest of the time, it just looks like smooth jelly motion. Okay. So, in fact, I'm going to make another ink called iteration, so. Alright. So, we have our X positions. This could have been its own class, to be honest. We could have had a list of, we could have had just an array of classes, and each one has an X position, Y position, velocity, acceleration. But I've stored it as 4 different arrays. So these are all of the X positions and Y positions, velocities and accelerations. So we're essentially making our own little mini rigid body here, right? And then each mesh is in here in the mesh object. Nowadays, I wouldn't do that. I'd just make one giant mesh object because you can combine meshes. I didn't know that when I wrote this, but it's not that much of a. I mean, it's a save, right? Because instead of right now when we got 2 meshes, we're gonna have mesh 1, and we're gonna have to modify this one's corner, and then mesh 2 overlapping. You know, so we've got way more lines than we need being drawn. Now, there's the same number of triangles, but it's just the more operations being done because this thing and here, right, this vertex is being placed twice by 2 different meshes. Okay. So, and by the way, just to make it clear, if you're not used to working with meshes, you know, it's what everything's made of, and it's got a triangle. Well, it's made of triangles. They're all made of triangles. Okay, so if you want this, then this is 2 triangles that look like that. Okay? And if you want something, well, actually, just go like that in it. Or, I mean, well, I'm not doing that. I've got 1 triangle there and 1 triangle there. Alright. But anyway. So, we've got our particle system, Splash, which we're currently not using, but we can rig it up if we get some. Then we've got the material we're using for the top of the water. The material I'm using for the top of the water is just, you know, it's just a bog standard. I don't even know. It's called water top. Let's look at it. It's purple. Well, I can make it whatever colour I want. Really. Could make it black. I kind of like it as purple, so we're going to leave it like that. Right. Then we've got our water mesh. So that's just the base mesh we're going to use for everything. And it's literally just a game object that's empty. And it has a mesh on it, right? It's got a mesh renderer. And a mesh filter. And the mesh filter has nothing in it. The mesh renderer has this water material. So like, if you see here, I can change this to, so that's the color, right? So for some reason I decided that we'd just spawn a bunch of separate game objects for that. Now here's our constants. We've got K, which is, you know, the Hooke's law, the spring constant for how these are going to return. So each one of these is a little harmonic oscillator, okay? And they have a K, and they have a damping factor, which is B, right? So we got K for KX, B for BV. Then we've got a new variable you've never seen called spread. And spread is how much the wave is gonna propagate. Like how quickly. So if we have more spread, the wave is gonna propagate more quickly. If it's got less spread, then it's not gonna propagate as quickly. So spread is essentially how much this thing yanks down on other things. Right, so we're not bothering with all that cos sine stuff, we're just working with a spread variable that will do everything we need. And then this Z is, well, that's just the Z position, which I apparently have put it right behind 0, probably so it appears in front of things, although that's not how things work. I didn't understand shader draw order back then. But anyway, so then we got the properties of water, which is the base height, which is the Y, you know, the base height is this. It's the point where we're wobbling around. We got the bottom. I also put left and width, which apparently don't use, and time, which I don't use. So then floaty zone, that's what I return for buoyancy, so the things float in the water, but we'll return to that in a moment. Right, so we've got, on start, we spawn water at the X position that you can specify, the width you specify, the B plus the height, the bottom plus the height, and the bottom. Okay, this we don't even use, but it just gives you the index of a certain position. Okay, that's splash, we're going to ignore that. Spawn water. Okay, so we've got the left for width, the top and the bottom. We set our width. Our global width is the width of this. Bonus exercise. Add a box collider to the water. Well, I've already done that. I've done the bonus exercise, so that's fun. Okay, so yeah, because I wrote this, I uploaded this so other people could see it. Well, it's been modified since then because it's in a game, but yeah, this is one of the few times that my code has been commented because we were made to comment it for the tutorials. Okay, so we've got the position of this entire, so it spawns the entire mesh, right? And the position is the left plus the width over 2, so the center, plus the top and the bottom over 2, so the middle, right? So this puts it in the very center. We add a box collider. This is terrible code. Oh well, I meant to do that. I meant to do that. Wait, I've forgotten how to do it. Is it that? Nope. Is it Control Alt? There's a way of doing this. There we go. Right. There. Magic. Wow, cannot resolve. Do you really have to get component to do that? C.get component collider 2D. Oh, it was a box collider, that's why. Okay, there we go. Right, so we have the C's offset, right, which is, okay, essentially we're just drawing the box collider there. Right, we have the offset is in the middle, there's no offset, the size is the width on the top minus the bottom, and it's the trigger. So that's going to make our box collider, which can splash. Then here's the important bit, here's where we make the mesh, right? So we count the edges, so the edge count is the width times 5, so I suppose we're just making 5 for every single one. The node count is the edge count plus 1, because there's going to be one more node than there are edges. Okay, so then we add our line renderer. So we just make a line renderer, which is apparently called body, and then I set the shared material rather than the material, so I can still edit it in the editor, right? We set the vertex count to the node count, so the nodes are all of these pieces, right? Which are invisible. But obviously, like, there's going to be fewer there's going to be fewer meshes than nodes. Because if you've got 2 nodes, you got 1 mesh. If you've got 3 nodes, you got 2 meshes. Right. So that's why this is +1. Okay. So we've got our x position, y positions, velocities, and accelerations for the node count, so the number of nodes, and then we've got our mesh objects, our meshes, base, bottom, top. Right. So for each node, we're setting the line renderer. So we set the y position to the top. We set the x positions to the left plus the width, because each one times I over the edge count. So it's, it's the left point plus from I to the max. So, 1, 2, 3 for each node. So let's say 1. So it's the width of one piece times 1 divided by the edge count to make sure that edge count is the total. It's basically making sure that they're linearly spaced and they're going to be the right size. right? Because it's variable width. Okay. So then we set the positions, the accelerations are going to be 0, the velocities are going to be 0, they're all static. Now we make the mesh. Right, so we make a mesh. I'm making lots and lots of meshes, but each one's a little mesh, and each one has vertices. The vertices are going to be the x positions of each node, right? So, you know, it's going to be the x position of this node is the left side, and then the next, and the y position is this node, right? So this node has an x and a y, right? And the top left of the mesh, the 0 point, so this is 0, right, is at the x position, so the left side of the first node, and the y position of that node. Okay, and z is just z. And then the first one is the x position of the node plus 1. So we get the next node, right? We draw around that. So this is x plus 1, y. Right? And then, well, I mean, we can just call that also has this x, y, right? But I don't know. We can call that x, I, y, I, x, I plus 1, y, I plus 1. Right? And so we got the y positions of I, then we got the x position. To be honest, the y positions are all the same, so it doesn't really matter that I've done that. But either way. Then the third vertex, right, so that's the first vertex. This is vertex 0, is the left side. Vertex 1 is this side. Then we got vertex 2 and 3 are here. Right? Or is it 2 and 3 this way around? Yeah, 2, 3. And you can see that these ones, the y position is the bottom. So the bottom's that side. Okay, so now we've got a mesh. Then there's the UVs. The UVs are, you've got your texture, and you want to map this texture onto this thing here. So your texture has its own UVs. Like, your texture has its own vertices as well, so you can call them 1, 2, 3, and 4 as well. Or like 0, 1, 2, and 3. And then it'll, you know, it'll map this corner to this corner of this mesh. If you were to instead use 0. You know, if you use this as your top left corner, then your mesh would map like this. Alright, so this thing would be stretched over this thing. But as it is, we just want the square. So you see, we've got, this is 0, 0, 0, you know, 0, 1, because it's at the top. Right, this is, we'll call this y position 0, and this 1. Okay, so you've got 0, 1, 1, 1, 0, 0, 1, 0. 0, 1 to the top. 1, because it's plus 1. 1, because it's the top. 0, because it's the bottom. 0, because it's the bottom. 1, because it's the next node. 0. I hope you followed that. I know it's a bit esoteric. And then you get your triangles. So the triangles show how it's going to render the mesh. So I've put it 0, 1, 3, 3, 2, 0. So these are the numbers. You can see 0, 1, 3. That's one triangle. And then the other triangle is 3, 2, 0. Right? So we've got our two triangles. Right, we've done it. We've made a mesh. Now we add all of this data to the mesh. Vertices, UVs, triangles. We create a holder for the mesh, set it to be the manager. Okay, we make some manager, whatever. Right. Now, when we have this function called update meshes, and we can call that any time, and it will do the same thing we've done there. Right, so it's just gonna go through all the meshes and it's gonna just draw its positions. So we can modify these x positions and these y positions, and then the mesh will keep, as long as we keep calling update meshes, it's gonna keep drawing them. Right? So then what we do is we have fixed update. This is where the actual physics enters the arena. So in here, we have look, we have force is kx, F equals kx, right? So k, the y position minus the base height, right? So if we, if we pull it up, if we pull this node up, then this is the x, right? If we pull it down by this much, this is our x. So that's the kx plus bv. Right, I've done plus instead of minus, but oh, there we go. Acceleration is minus equals force. Now, obviously, that's not very right to say that because there's no mass, but, obviously the mass is being called 1 here. So, we have some force. Now, what I really don't like about this is this is using the Euler method. Because we've got y positions plus equals the velocities, then velocities plus equals accelerations. Let's flip that, and we should actually, now it should be using the Euler-Chroma method, which is consistent with the rest of Unity. Because if you do the velocity first, yeah, I mean, you're not going to notice the difference, but it's less likely to go haywire and explode everywhere. So, right. Also, I don't like that this isn't times by delta time. It should be. So let's do that. But clearly that's going to break the way that I balance this. So then we'll divide it by, we'll times it by 50, because that must have been how I originally intended it to be. That's the FPS, right? Right, so now even if I slow down time, this thing's still going to work. Okay, so we've got body as set position. Now here's the important bit, the new physics that we've not seen before, because we've seen this before, right? It's just a spring. This time we're going to make a list of all the deltas. So that's the difference in heights between this and the one on the left of it. So if I have a thing here, right, and another node here, we can look, okay, I'm here, and there's a position to the right of me, and this is the delta in height, right? So we'll call that the D on the right, and then there'll be one on the left, and we'll call that the D on the left, right? So we're going to go through all of them, and as long as I is greater than 0, because obviously there's no left delta on the leftmost one, and there's no right delta on the rightmost one, right? We take, because just to be clear, if you're on the very left one, there's no left delta because there's nothing on the left. If you're on the very right, there's no right delta because there's nothing on the right. So we start from above 0 and less than, the length minus 1. We make 8 passes, so I can call this iterations. You see I added that at the top earlier. Iterations equals 8. That's forward thinking. Right? Then what we're going to do is we're going to make an array of all of the left deltas. So that's our spread value times by the difference in height. Okay. And then we've got, I mean, I don't like what I've done there. Velocities plus equals the deltas. Let's do, I mean, it's plus the position. I really don't like what I've done there at all, because it doesn't make any sense to add a position to a velocity. But clearly, this is making some kind of force. So it's essentially like a, oh my god, it's like if you're adding the position on, but because you're adding it on, it's an acceleration. So it's essentially kx. This, it's almost like kx, but it's the kx of the side. So in fact, if we times it by 50 and times it by time.fixed delta time, it's, this is essentially a force now, and it's a force based on k. Right. So that's less egregious to me. I don't mind that anymore. Okay. So now we've stored them all. We stored all the left and the right. Now we're going to apply a difference in position. I hate this. I hate what I've done here. I actually despise what I've done here. But I've just added the positions on of the left deltas on the right deltas. But it works. So I take the y positions of I minus 1 and plus equals the left delta. Okay, so I basically take the 1 to the left and drag it up by the left delta, and I take the 1 to the right and drag it by the right delta. Okay, which I really shouldn't do. I should just modify their velocities. But, I mean, it works. So, I don't want to edit this right now, because it's going to break everything. And then we update. Right, so that's... And then we get this behavior. Right, what I wanted to say is... Okay, first of all, I want to check one thing, is the iterations. Because if we take... Let's put more... Let's, instead of using... Is it not public? This... No, it's private. I wanted to see what happens if I just use less iterations. You can see what will happen. We're basically doing it lots of times because it'll make the simulation more accurate. So here, we're only going to do it one time. You see that? Right. Now let's put up the iteration count. There, it's on 3. And let's do 4. Let's do 6. It's starting to get smooth now, right? Let's do 8. Let's do 16. This is going to be really slow. Yeah, there we go. Now we get rid of that. So you can see we still have that initial drop though. So my solution to that, if I look at it, is going to be, well, when it hits, on collision enter, it causes a splash, right? What if in splash I call fixed update? I think that should solve the problem. Wait, sorry. Well, no, apparently not. Splash. Is this where it happens? Water detector. Splash, yeah. Well... Okay, I guess that doesn't work. I was hoping that if I just... Because the problem is, right, this one only affects the velocity of 1 point. So the splash effect, right, it looks at where your position is. So it takes your x position, it takes your velocity, right, and then it says if your x position is within the bounds of the left node and the right node, then it'll find the closest one, right, it finds the index of it, give a y velocity to the thing. But when it gives y velocity, it doesn't give velocity to the others. Ah, well, that's a problem. Well, you'd essentially need to give velocities to the other ones around it as well, with some kind of spread there. But we don't have time to do it because it's already lecture end time, isn't it? But you can imagine how you could do the same thing here, right, that I've done with the spread, except you could spread the velocities just in this initial function. Or you could grab the indexes around it, you know, instead of just pushing one index, you could go, well, velocities index plus 1 plus equals velocity over 2 index plus 2 4. Okay, and then we're gonna go -1. Obviously, I'm not doing the checks here to make sure that your array is within the bounds, so I'm gonna be careful where I click. But no, we should. You see, now it looks better. One other thing I wanted to change in this is so there's the buoyancy, right? And all the buoyancy does is kx minus bv, right? And if it on collision stay. So I've got this spawn rock, right, which just spawns a rock. You click on mouse button down, it looks at the world position, the mouse position, and it spawns a rock, right? Now the buoyancy is from the water detector. On trigger stay, it will do that, right? The buoyancy adds kx minus bv, right? So the problem is it doesn't actually respond to the water, right? They will just bounce to this base level, but they're not actually bothered where the water is. You could pass here, like the height of the position it's in as well, right? So here you could grab. Well, this thing has get index, right? What's it returning? It's returning the y position. Yeah, we could grab the index of the water, get index at the collision point, other dot hit, other dot contacts. What would it be called? Contact point. Hit dot contacts. What's wrong with that? Someone remind me. Normal. Why is it get contacts? Yeah, I know, but it's a it's a collider. Yeah, it's not the Well, how do I get the contact points of it? Oh, I could just get the position of it, right? But you'd think I could get the yes, but you can't. Well, you can take the x position of this thing, right? Now this is complaining because this thing doesn't have on the rigid body what to tell me. Yeah, but it'll tell me where the contact points are of the thing, but it won't tell me like where it hit this, you know. So, but I can grab its x position, right? So, grab the x position of this thing, go in here, that's giving me the index, and then instead of adding this height here, we could have like, instead of the height, it's this height plus, well, sorry. Let's just try putting it a y. I don't know if that'll work. But now maybe it's going to be directed at the height of this thing instead. Yeah, I think kind of. But what I'd need to do is add something to it, right? Because the stronger the gravity is going to be, the less the buoyancy is actually going to be able to correct for this. So if we go 1.8. Yeah, because you can see now when I drag it, the other ones are being pulled down as well, right? So it's kind of to some extent working. Right, it's at least doing something. But clearly you'd need to tweak these values. Because maybe, you know, for a start, maybe the on the ball itself, you need to increase K. So it gets yanked more. Hey, look at that. Well, now because K is increased, that's making problems with this height formula. So you'd have to balance it. You basically have to have your own y variable to correct for its own gravity. Or you could add on the gravity force, which would also work, you know, but anyway, you get the point. Right, we've run over anyway. As usual. So, any questions? Oh my god, it's on the Hong Kong video. Is it actually rubber? Because the person I was with just wanted a video for Instagram, didn't care about physics. Could have waited a little bit longer. Here we go. Right, so this is in Hong Kong's Museum of Science. Right. You can see what's happening here is there's a sound wave. Can you hear sound? You can't hear sound from my screen, can you? I'm gonna turn sound on. So everyone be quiet or your voice will get recorded. Right. I'm recording desktop audio now. So here we go.
But it's like multiples of each other, so I'll have half that again against 20 Hz. We'll see it again, but even more spaced out. Watch.
Right. So what I just said there was yeah, you won't be able to hear it. You'd only be able to hear it on the video afterwards, right? So yeah. So what I say is I say something like, oh yeah, once you get to 20 hertz. So clearly this thing is multiples of 40 of like 80 hertz, right? So like 20 hertz, 10 hertz, 80 hertz. So I think this thing, it must be at 40 hertz right now. That's why it sounds so bassy, or maybe 80. And right, so what happens is in a harmonic oscillator, everything on Earth, every material has a natural frequency, right? So it has a frequency it wants to be oscillated at, and you hear this sometimes especially if you like bassy music and you play a lot of bass. Sometimes a certain bass will rumble your whole cupboard, and you're and like you're so. And sometimes you'll play a piano or something, and you play a note, and like you'll hear something buzz in the room. Now the reason that happens is when you drive an oscillation, like when you press a piano key down, you're driving an oscillation. When you drive, and they're called forced oscillations. Okay, forced oscillations, hyperphysics, right? And when you drive, right? When you have a driven oscillator, it works a bit differently, right? If you happen to drive something at its natural frequency, you get resonance. Resonance is when you drive something at its perfect natural frequency. Oh, look, you can. It works with swings. I didn't think about that. Okay, look, it's easy to get an object to vibrate at its resonant frequencies. It's hard to get it to vibrate at other frequencies. A vibrating object will pick up its resonant frequencies from a complex excitation and vibrate at those. Yeah, so essentially, if you vibrate at many frequencies, it will end up like cutting out, filtering out the other ones. And most vibrating objects have multiple resonant frequencies. So what happens is, if you as a general rule, if you resonate something at double the hertz, right? If you double the hertz rate, it will resonate again. So you don't actually get to see it in this video because she killed the video before I demonstrated it, annoyingly, right? But you can see here that these things, this is creating a standing longitudinal wave, right? So we're just, these things are just bass underneath it, right? So we're shoving some bass speakers up, and like this thing, well, actually that might just be a block that holds it up. But these things, the sound is making these things jump into waves of their preferred natural frequency, and you can see that, you can physically see the sound wave, right? That's how sound waves work, right? At the end, I actually turn it down, and yeah, you see here, like when let me mute this because when you at the end here, I turn it down, right? But then what's going to happen is when I lower it to 20 hertz, right, from 10 hertz, it's going to lower the number of waves. So like what did happen if you actually watched at the time is this thing went from this to this. Right? So right now you can see that it's like, so this is 40 hertz, right? I don't know if the amplitude would be bigger or maybe the same. I've never thought about it. It might be that the amplitude's bigger at the low ones, but that might be wrong. So don't read the amplitudes. Don't think that that's right. But then, so that's like, the red is 20 hertz, the blue is 40 hertz. Then at 10 hertz, it would be like this. Right? And then at like 80 hertz, it would be like this. So once you get to really high hertz levels, you're not even going to see it anymore. It's just going to be a wibbly wave, right? But the point is, it's really cool. You can just see that in person, and you can just watch how the sound vibrates this into, you know, they stand up in these little mountains. It's a pity the Hong Kong video wasn't longer. But yeah, the reason I wrote Hong Kong video down was I was going to teach you resonance, but it's just like, you aren't going to use resonance, right? Like, you're not going to stick natural frequencies on your objects. And if you do, then well done, and you can, and go on hyperphysics and figure it out. But, I mean, it's not that hard. You just, well, you can look it up online. But there's no point me teaching an entire class of people how to simulate resonance in a game engine when you're never going to use it. In fact, I mean, I doubt most of you are going to use this water stuff, but at least this thing, you know, I could see some of you using this if you were making a 2D platformery type game, right? This is somewhat useful, right? It's and even if this specific example isn't useful, you've seen the method now. You understand the spread method. It may not be water that you're dragging around. It may be a series of springs, or like you may have things connected to each other you want to drag down, and you now see the way to do it is you make your left data array, your right data array. If you've got 3D, you can do your forward data array, your back data array. Then you're going to calculate them beforehand. You don't immediately apply the velocities, otherwise it's going to mess this one. So you make all the arrays first over the entire system. Then once you have all of your deltas, then you start dragging stuff. So either by applying velocities or by physically dragging them, which is what I did there, which is stupid. But yeah, that's that. I assume. Well, have we got any more questions, or is that?